In this video, we'll be talking about how do you go about designing your databases so that they don't run into particular problems like anomalies or redundancy. We'll talk about what those mean in a little bit. Okay, so let's look at this particular database here. It has columns name for the student's name, the team, every student is in a team, or it says a null value, and it has a grade. Every team has a particular grade shared by all the members of that team. Maybe I'm assigning a grade to a project turned in by the team. All of the students will get that same grade here. Okay? And so the data here is, for instance, Josh here is not in any team and hence doesn't have a grade, so I stick null values in there. Tyler and Han Chen are both in the team TA's rule. Charles is in the team The Auditors, and Anna and Emily are in the team Lady Debugs. And now the important thing to note here is every team has a particular grade, and all the members of that team have that same grade. And so this is a good example of where we can do what's called a decomposition, where we can break up this relation into two sub-relations that has the same information, but it doesn't have some of the redundancy here. So the big piece of redundant information here is the fact that every team member has the same grade. So for instance, I say in the top example that Tyler has a 3.0 and Han Chen has a 3.0. I don't need to say that twice. I can just say everybody in the team TA's role has a grade of 3.0. So what I can do is I can break up this relation into two sub-relations. I have the relationship that has name and team, which I might call something like team membership, and it just says for every student what team they're in. And then I have another relation which has the rows team and grade, and this holds the information of what did each team get as a grade. And so I can say TA's rule got a 3.0, the auditors got a 3.7, and Lady Debugs also got a 3.7. This is an example of a good decomposition. Why is it good? Well, for here, there's no more of that redundancy. And the other nice piece about this thing is that I can join these two tables together and get back the original table. If I just do a simple join between these two tables, I'll get back the table on the top. Okay, so this is a good decomposition. What is a bad decomposition? A bad decomposition would be something like this. So let's say I kept the same, each team got a grade, but on the left side here, I have name and grade. I say Josh got a grade of null, and Tyler got a 3.0, Han Chen got a 3.0, Charles got a 3.7, Anna got a 3.7, Emily got a 3.7. Now this is a bad decomposition. Why? Because I've lost information here. I no longer know what team Tyler is in. All I know is that he got a grade of 3.0. And the fact that, Charles, which team is Charles in? Well, Charles could be in the team The Lady Debugs, or he could be in the team The Auditors. I have no way of knowing from this information. There's no way for me to join these two tables together and get back all of the information in the above table. So this, in our attempt to try to remove redundancy, we've actually broken things badly. And so what we're going to be doing basically for the next 2 weeks is figure out how to do good decompositions to achieve the sorts of things that we want. Okay, so the two parts of a good decomposition are, one, you should be able to recover the original relation by doing a natural join on the subrelations. Okay, meaning that if I take these two tables and join them together based on column names, I should get back the original relationship. This is called a lossless join, meaning when I bring them together, I get back all of the information. I haven't lost anything from the original relation. Okay? This is the most important part. Okay? And so why do we do decompositions? Well, decompositions are necessary to do two things. One, to guarantee correctness. We want our databases to not be able to hold bad data. And it's also important for performance reasons. Okay? That's why we want to design our databases to be smart. And so what is bad design? Well, bad design is anything that makes it hard to achieve those two things. It makes it hard to achieve correctness, it makes it hard to achieve performance. Okay? And so often, and there are many types of bad design, but the bad design that we're primarily focused on right now are that bad designs can often lead to redundancy. And redundancy leads to inefficiency, meaning you have to have space for this redundant information, meaning you have slower performance. And so you're wasting both memory and time because memory is time for many of these operations. The other bad thing is redundancy can lead to anomalies. And anomalies are scary and sound bad because they are. Okay, so what are anomalies? Well, Once again, redundancy is information that's repeated. So in the previous example, some of the information that was repeated was the fact that even though each student in a particular team had the same grade, okay, so we repeated that grade information for each team member. And anomalies are problems that occur if you have redundancy present in a relation. And there are two types of anomalies that we're really concerned about. The first one is called the update anomaly. So for instance, say we change information in one tuple, but we don't make the changes needed to other tuples. What would be an example? Let's say I need to give the team TA's rule a bonus point. Okay, I found out, I accidentally graded them wrong. I need to give them an extra point. An update anomaly would be if I update Tyler's grade, but I accidentally didn't update Han Chen's grade. And so now I have an anomaly. Tyler and Han Chen should have the same grade because they're both in the same team, but because I only updated one of them, I now have an anomaly, and my database is now screwed up. It doesn't hold that rule that I said everybody in the team has the same grade. Another problem is a deletion anomaly. Say we want to delete a row, and we might remove information that we wanted to maintain. Okay, so in the example, let's say Charles drops the class, okay? However, I don't have any way to show that Charles dropped the class without also deleting all the information about his team as well. He was the only member of the team, the auditors, but if I wanted to keep his team grade around, I don't have a good way to do that. So, multiple choice question time. If you aren't allowed to choose the schema, if you aren't allowed to design the database, how can you make sure that anomalies don't happen, by people doing stupid stuff with update or delete or adding in data that's not valid? So actually, all of these can work, though they're all a pain. Okay, so the first one is you're only allowed to modify the table using approved stored procedures. You design the stored procedures to make sure that whenever somebody needs to drop the class, that it changes the database in the appropriate way to keep the information you want. And you make sure that if you need to add a bonus point to a particular grade, it changes all of the necessary rows. So that's one way to make sure that anomalies don't happen, by basically enforcing the rules by saying everybody use these stored procedures, which guarantee that these things happen. Another way, a very similar way, is to add triggers on like insertion, deletion, and update that will check and raise an error if somebody tries to do something that's not allowed. Like somebody tries to add in, tries to say change the grade for a particular member without also changing the members for other things. Another way to do this is to add check constraints by basically saying, okay, this table, all of these rows must always match all of these values must always be the same, and you can add check constraints on the table to make sure that is always the case. The other option is you just use threats and to keep people in line. But in reality, all of these are really messy ways to ensure that anomalies don't happen. The much better way is to design your database such that the normal sorts of changes to your database are only able to happen if the change makes sense, and by doing that is by doing a logical decomposition of complicated relations into subrelations.